So what we're going to look at today are graphical representations of motion. And the plan for this hour is to talk about and then practice creating and interpreting graphs of distance versus time and velocity versus time. And we're just going to restrict ourselves to objects that are moving in a straight line, so we call this one-dimensional motion, but we just want to kind of practice these ideas. The rationale is because a lot of times we physics teachers tend to focus on the equations and solving equations. And to be successful in the AP exam, you really have to sort of understand intuitively how the graphs connect to the equations and how to work with multiple representations. So that's kind of the idea behind this. So we'll kind of maybe connect some of those dots. All right, so as you probably know, if you graph position versus time for an object moving in a straight line at a constant speed, the graph looks like this. And if you were to find the slope of the line, slope we know is the rise, so in this case delta x divided by the run, which is delta t. Delta x over delta t is what we call the average velocity for that interval. And so we started off by talking about velocity as the change in position divided by the change in time, or displacement divided by the time. And that's exactly what we're doing here. So the first big idea we want to get to is that the slope of a position versus time graph is the velocity of the object. So finding the slope is finding the velocity. So if you have a position versus time graph and you're asked questions about the velocity, what you're really being asked about is the slope. So if the position of an object is given by this graph here, which has 4 segments, then we can kind of figure out what's going on. During this first segment right here, the object has a positive velocity, and it's quite large because this slope is quite large. It's a steep slope. So the velocity is positive, it's moving fast to the right. In this next section here, it is still positive, but it's not quite so steep. So we could say that the velocity is smaller, but it's still positive. Here, the slope is 0, and so because the slope is 0, the object is at rest. And that sort of makes sense because as time goes on, from here to here, the position doesn't change. The object stays in the same location. And then here, the slope is negative, which tells us that the velocity is negative. The object is moving to the left. All right, so position versus time, the slope tells you the velocity. The slope can be positive if the object is moving to the right. It can be negative if the object is moving to the left. So here's a chance to practice this idea. Suppose you're given a displacement versus time graph or a position versus time graph, and it looks like this. So what we'd like to do at this point is just have you pause and see if you can think up a story that that is explained by this graph. So maybe make it a fuzzy or a furry mammal and think about the velocity. So take a minute to pause the video and figure out what the velocities are for each of these 3 segments, and then see if you can fit that into some kind of narrative. And then come back and I'll give you an example, and you can see how close yours was to the physics. Of course, you might have a different mammal. Okay, so now we're back. So during this first segment, the object is moving to the right, and the slope, which is the rise over the run, is 0.33. So the graph goes up 5 meters during the 15 meters of time that elapsed, so 5 over 15 is 1/3. So whatever it is, it's moving to the right at 33 centimeters or 0.33 meters per second for 15 seconds. In the second segment right here, it's at rest, and that lasts for 5 seconds. We can tell that from the graph. The slope is 0, and that happens for 5 seconds. And in the last section here, the displacement is negative 5 meters divided by 5 seconds, so that's negative 1 meter per second for 5 seconds. So perhaps your story is about a mouse who slowly creeps out of his hole at a position of 0, and he ambles across the floor a distance of 5 meters where he finds a piece of cheese. He nibbles on the cheese for 5 seconds, not moving his body, and then he spies the cat and he hustles back pretty fast for a mouse at 1 meter per second, all the way back to his hole. So that might be a story that is consistent with the graph here. So the idea is slope is velocity when you have displacement versus time. Now, what would happen if your position versus time graph looked like this? Here, you have a small slope. Here you have a bigger slope, and here you have an even bigger slope. The slope is increasing. Well, if the slope is increasing, since the slope is the velocity, then we know the velocity is increasing from here to here, and then it is moving faster and faster. So what we can tell from this idea is that if the graph is curving, then the velocity is changing, because a curving graph means the slope is changing. If the slope didn't change, this graph wouldn't curve. So clearly the slope here is different from the slope maybe over here, which is different from the slope here. So the slope, the velocity is changing, and that's what we call an acceleration. So on a position versus time graph, not only does the slope tell you the velocity, but if the slope is changing, you can tell that it's accelerating. In this case, the slope is increasing as we move from left to right, and so the velocity is increasing, which is a positive acceleration. So think about this graph here. This is a position versus time graph. What is going on? Well, look at the slope at the beginning. It's positive and quite large. Like from here to here, the slope is about 2. And then later on, the slope gets smaller. In here, it's about 1. Here, the slope is about 0.5. Here, maybe it's 0.1. And so the slope, the velocity, is decreasing. So in this case, the object starts out with a positive velocity, which decreases, and this is kind of flattening out. Eventually, this might get to 0. The object is slowing down, and maybe eventually will stop. Okay? So this graph, the curvature of this graph, tells us that the velocity is not staying constant, it's accelerating. And in this case, the acceleration is negative because the velocity is decreasing. Okay, so just kind of think through the slope. Look at any one section and think about its slope, and then move over a little bit and think about the slope again. Is the slope greater or less? If the slope is less, smaller, then the object slowed down, the velocity decreased. All right, so here is a practice multiple choice question. Which of the following graphs show an object that is moving to the left with a positive acceleration? So here's 4 graphs. So take a second, pause the video, think about that, choose your best answer, and then we'll talk about it. Okay, so the object is moving to the left, so the velocity must be negative, so the slope must be negative. So which of these graphs have a negative slope as you move from left to right? Well, B has a negative slope, and C has a negative slope. D and A both have positive slopes. So if that's confusing to you a little bit, think about riding your bicycle on the graph from left to right. If you're going uphill as you go left to right, that's a positive slope. And if you're going downhill, that's a negative slope. So it's either B or C. Now we got to figure out. It has a positive acceleration. That means that the velocity must be increasing. So here, the slope is like maybe -1, and then -2, and then -3. This slope is decreasing. It's becoming more negative, farther to the left on the number line. Here, the slope is a negative value, like maybe -5, and then -3, and then -2, and -1 as we get down here. Going from -5 to -1, for example, is increasing, so that has a positive acceleration. So the correct answer here is B. Graph B shows an object that is moving to the left. The velocity is negative, but it has a positive acceleration. It's getting larger. Okay, so that was displacement versus time graphs. Now we're going to take a look at velocity versus time graphs. So on a velocity versus time graph, the slope actually tells us the acceleration. So in this case here, the velocity stays the same the whole time, and that means the acceleration is 0. If on a velocity graph, the graph looked like this, then the velocity is increasing as time goes by. So here the velocity, let's say we just use this, let's say right here the velocity is 1, and then here the velocity is 2, and a little while later the velocity is 3 and 4 and 5. The velocity is increasing. This is a positive acceleration. So if we graph velocity versus time, the slope tells us the acceleration. In this case, the slope is positive, so the velocity is increasing. If you had a line like this, you would have a negative slope. That would be a negative velocity. Excuse me, that would be a negative acceleration. The velocity is decreasing in this case. So velocity versus time graphs are actually really useful. The slope of the graph tells us the acceleration. But there's something else useful about velocity versus time graphs. And this comes from calculus, so ask your calculus teachers about this. Not only does the slope tell you the acceleration, but the area under the graph actually tells you the displacement. Okay, so this has to do with the fact that the slope of a displacement versus time graph gives you the velocity, and so the area under a velocity versus time graph tells you the displacement. So if you have a graph of velocity versus time, not only will the slope tell you the acceleration, but this area underneath the graph, it tells you the displacement, how far the object has moved from its starting point during the interval of time of interest. Okay, so let's just take a look at that. Suppose you have a car going 4 meters per second, and it stays at a constant velocity of 4 meters per second for 20 seconds. So what you're actually doing to figure out how far it goes is you're finding the area under this graph. We're finding the shaded area. So if it's going 4 meters per second, then in 1 second it'll go 4 meters. So that's this area right here. In 2 seconds it'll go 8 meters. That's this area here. And in 20 seconds it will go 80 meters. So the area under this graph can be found by taking the height of the rectangle times the width of the rectangle. The height of the rectangle is 4 meters per second, and the width of the rectangle is 20 seconds. So if you take 4 meters per second times 20 seconds, you get 80 meters. So the area under this graph is 80 meters, and that's how far the object moves. You might remember this as simply the distance an object moves is equal to the velocity times the time. If we take 4 meters per second and we multiply that by 20 seconds, we will go 80 meters. So what we really found was the area under the graph. Okay, so velocity versus time, it's a really useful graph. Its slope tells us the acceleration, and the slope right here is 0. So the acceleration is 0. And the area under the graph tells us the displacement. So let's try to solve a problem using this idea. Suppose we have a car. Initially it's going 5 meters per second, but it accelerates to 13 meters per second in a time of 4 seconds. I want to know what is the acceleration of the car and what is the displacement of the car during this interval. Okay? And we're going to try to do this without any of our physicsy equations. All right? We are just going to graph this velocity. So the initial velocity is 5, the final velocity is 13, and it does it in 4 seconds. So the graph will look something like this. We start at 5 meters per second, and we speed up to 13 meters per second in a time of 4 seconds. Okay? So just using our graphical representation, we can find the acceleration because it's the slope of this line. So the slope of this line is the rise. It goes up 8 units from 5 to 13, and that's divided by the run, which is 4 units. So 8 over 4 is 2. So the acceleration is positive 2 meters per second squared. And you could have solved that with equations, but we're just looking at how to do it graphically. Okay, so the acceleration of the car is 2 meters per second every second. Okay, so you can think about it this way. If you're going 5 meters per second, then 1 second later, you'll be going 7. And another second later, you'll be going 9. Another second later, you'll be going 11, and another second later, you'll be going 13. Your velocity is increasing 2 meters per second every second. That's the acceleration. It tells you the rate that the velocity changes, and it's the slope of the velocity versus time graph. Now, our second question says, what is the displacement of the car? How far has it traveled? So in this case, if we have velocity versus time, the displacement is the area under the graph, which I've shaded. And I've shaded it in blue and purple to help you see that there's really just 2 shapes here that we need to find the area of. The area of the purple rectangle here, we can take 5 times 4, which tells us that that area is just 20. And the area of the blue area here is a triangle. So we need 1/2, the base, which is 4, times the height. It goes from 5 up to 13, so the height here is 8. So the area is 1/2 the base, 4 times 8, which is 16 meters. And so the total displacement of the car we can find from our graph is just 36 meters. The car goes 36 meters while it's traveling. So we don't really need all kinds of fancy equations. We just need to know that the area under a velocity versus time graph tells us the displacement. Now, you might be wondering how this connects to the equations, because you could have solved it with equations. So here's kind of a neat little connection. The area of the purple rectangle is just the initial velocity, 5, times the time. So v0 times t is how far the car would have gone if it kept going its initial velocity. But we're going to go extra far because we're speeding up. That's this extra area up here. And that's a triangle. So that's 1/2 the base. So here's 1/2. The base is t. And then the height, this height here, is really just the distance in delta t here, times the slope. So delta y equals the slope times delta x is what we're using here. So it's just the acceleration times the time tells you how much this goes up. If you're going up 2 meters per second, 2 meters per second, and you do that for 4 seconds, you go up 8. So this is the height of the rectangle. So you can write this as 1/2 a times t squared. And so this equation, which you use and which is on the AP reference sheet that tells you how to find the displacement of an object, is really just telling you how far it would go if it didn't accelerate, and then how much extra it goes because it does accelerate. Okay? And because we found this using the area of a triangle, this only works when this is a straight line here, which is why we can only solve problems for accelerations that are constant, when we have a slope here that doesn't change. If this slope were to curve here or something, you would need calculus to find the area under the graph, and we're not doing that. So those are where our equations come from. And of course, the acceleration is the change in the velocity divided by time, and that's just another way to say it's the slope. Okay, so that's the connection of those graphs. This doesn't really show up on the AP exam, but it's just a fun fact. If you graph acceleration versus time, then its slope is called the jerk. And if you graph the jerk versus time, its acceleration is called the snap. And you can do fun things with these with calculus, but we're not going to worry about those right now. The most useful one is graphs of distance versus time and velocity versus time. So here's kind of a summary, okay? So end of lecture. When the motion of an object is represented on a displacement versus time graph, so this is x versus t or d versus t or delta x versus t, anytime that happens, the slope of the graph tells you the velocity. When the motion of an object is represented on a velocity versus time graph, then the slope tells you the acceleration, and the area under the graph tells you the displacement. So this is kind of a doubly important one because you can find out all kinds of neat stuff from the velocity versus time graph. Okay? So, quick note, make sure you know what kind of graph you're looking at. Suppose I asked you for the displacement of the object at 23 seconds. So you're going to go over here to 23 seconds, and you're going to say, what am I being asked for? So here's the way to think about it. If you're asked for the displacement, and you're looking at a graph of the displacement, what we're really asking you for is just the value of the graph. So over here at 23, the value of the graph is simply 2 meters. The displacement at 23 seconds is 2 meters. But if I ask what is the velocity of the object at 23 seconds, now over here at 23 seconds, if you're looking at a graph of displacement and I ask you for the velocity, I'm really asking you for the slope. So I'm asking you for the slope right here. And the slope right here is the same as the slope of this entire line segment. So you can find the slope of this line segment. The rise is -5 meters. The run is 5 seconds. So it's -5/5, which is just -1 meter per second. So when you're asked about a graph, just make sure you know what you're being asked. Are you being asked for the value of the graph or the slope of the graph? Okay? So just make sure you take a look at which graph you're looking at there. All right, so let's put this all together in a free response question. So I'm going to kind of go through this, and anytime I ask a question, it'd be helpful if you just pause the video and thought about the answer, and maybe even try to do it on your own, sketch the graph, before continuing and seeing the answer, because physics is not a whole lot of fun if you're just a spectator. It's more fun if you're a participant. So jump in and try it with us, okay? I've got a car going 25 meters per second. The driver drives at this speed for 3 seconds, and then they might see a fuzzy enamel, perhaps, and they hit the brakes, and they come to a stop in 5 seconds. So I want you to do 4 things. I want you to represent the motion of this car on a velocity versus time graph. We're going to use that graph to find the acceleration. We're going to use the graph to find the displacement of the car during the time that it's in motion. And we're going to try to sketch the acceleration versus time graph. So we'll break this into 4 parts. Okay, so here's the first part. Pause the video if you can, and see if you can sketch the velocity versus time graph for this setup. Okay, so maybe just get out a pencil, try a piece of paper, make a sketch. Okay, so here's what it looks like. The car is going 25 meters per second for 3 seconds. So our velocity remains 25 meters per second for 3 seconds. And then it decreases at a constant rate over the next 5 seconds until it reaches 0. Okay? So that's what the graph of the velocity versus time looks like, and we can get that from the way the problem is worded. So for 3 seconds, it maintains a constant speed of 25 meters per second, and then during the next 5 seconds, it comes to a stop. All right? So that's the first question. So the second question says, use the graph to find the acceleration of the car during the time the brakes were applied. So the brakes were applied during this segment right here. So if you are looking at a graph of velocity versus time, how do you find the acceleration? Well, you're going to find the slope. So go ahead and pause the video and find the slope of this segment right here. That's the acceleration of the car while it's braking. Okay, so it turns out to be -5 meters per second, or meters per second squared. That's the acceleration. That's the slope right here. So the graph decreases 25 over the 5 seconds that it takes to do that. So that's -25 over 5. Okay? All right. Part C says use the graph to find the displacement of the car during the time it is in motion. So it is in motion for 8 seconds, and if we're finding the displacement of the car, we've got to find the area under this graph. So here's where I'd really like you to stop the video, see if you can find the area under the graph. If it helps, think about dividing the graph into 2 sections. We have a rectangle here and a triangle here. Go ahead and pause the video, find the area of those 2 sections, and that will tell you the total displacement. Okay, so for section 1, this is 25 meters per second high, and it's 3 seconds long. So 25 times 3 gives me an area of 75, and that's going to be in meters. Meters per second times seconds is meters. So the car goes 75 meters during the 3 seconds it's coasting along. Now, we got to find the area of this section. That's 1/2 the base times the height. So that's 1/2. The base is 5, so that's there, and the height is 25. So you can put that in your calculator, or you can probably just think about it, and that's 62.5 meters. So the car goes 62.5 meters while it is slowing down. And so the total displacement of the car while it's in motion is simply 75 meters plus 62.5 meters, or 137.5 meters. Okay? Now, you can solve that problem completely with equations. But it takes a while, and you got to break it into 2 parts, because the acceleration here is 0, and the acceleration here is -5. So you've got to break it into 2 different problems and find the distance it travels in each segment. And you can see from the graphical approach that it's really easy to understand what's going on if you think about the velocity versus time graph, and the slope being the acceleration, and the area under the graph being the displacement. Okay, last thing. See if you can sketch the acceleration versus time graph for this car. So if we back up, during the first 3 seconds, what was the acceleration? And then during the last 5 seconds, what was the acceleration? And plot those on a graph that looks something like this. So sketch a graph, acceleration on the y-axis, time on the x-axis. See if you can do that. Okay, so for the first 3 seconds, the acceleration was 0. So we plot 0 for 3 seconds. And then for the next 5 seconds, so from 3 until 8 seconds, we plot an acceleration of -5. So the acceleration graph looks like this. And in AP Physics 1, all your acceleration graphs will only consist of horizontal line segments, because we are only solving problems where the acceleration is constant, not where the acceleration is changing. So you will never have an acceleration graph that increases or decreases, for example. It'll just be horizontal line segments. So during the first section, it was 0, and then acceleration was -5. Okay? All right, here's another practice problem just to think about. If you have velocity versus time, how do you find the acceleration? Well, you find the slope. So test yourself. Hit pause, see if you can find the slope on a couple of these sections, and tell me what's going on with the object. Okay? And when you get that done, hit play again and see how you do. So here's my solutions. During the first section, the object is accelerating at 2 meters per second squared. During the second section, right here, the acceleration is negative. The velocity is decreasing, and it decreased quite rapidly, so the slope is -4. The acceleration is -4. Then the velocity increases again. Then the velocity decreases all the way to -6. And then it increases again, finally ending at 0. So this object is moving to the right pretty fast. It moves to the left really fast. It moves to the right, this object velocity is increasing at a high rate. It decreases at a very high rate. It increases again, and then it decreases all the way to here where the velocity goes negative. So it's at this point where the velocity becomes negative, and then it increases again until it's back to 0. Okay, so that's what that graph tells us. If we were to plot the acceleration versus time for that graph, during the first 5 seconds, the acceleration is +2, so we would plot +2 as the acceleration. During the next segment, which is 1 second long, the acceleration is -4, so it's -4 down here. Then during the next section, it's 0.75, and so on. The acceleration graph looks like this. Okay. All right, so this is a tricky question. And the AP seems to like questions like this, at least from looking at past year's questions. How many times does this object change directions? So you desperately want to think that every time you see one of these corners in the graph that it changed direction. But that's not actually true. So think about the velocity. Here the velocity is 1, 2, 3, 4, 5. The velocity is 6, 7, 8, 9, 10. And when it gets here, the velocity goes from 10 down to 9 to 8 to 7 and 6. It's slowed down, but it's still positive. It's still moving to the right. And then here it's moving to the right still. It doesn't change directions until it changes sign. So right here the velocity is positive, and right there below it, the velocity is negative. The velocity changed sign right here. So at this point right here, at 13 seconds, the object changed directions. So this only changes directions once. Okay, so that's something that seems to come up a lot. How many times does the object change directions? It changed acceleration here, but it didn't change direction. It was still moving to the right. It's moving to the right as long as this function is positive. And it changes sign. The function changes sign right there. Okay. Here's another interesting question. When is the object speeding up? So an object is speeding up if its velocity is positive and getting larger. So it's speeding up from here to here. Okay. During this section, it's slowing down. Here, it's speeding up again. Here, it's slowing down. But something interesting happens right in this section right here. The velocity goes from 0 to -1 to -2 to -3 to -4 to -5 to -6. It is speeding up in the opposite direction right here from 13 to 15 seconds. Okay? And then here, the velocity is increasing. It's going from -5 to -4 to -3, but the speed is decreasing. It's going slower and slower. So one way to think about this is if the graph of the velocity versus time is moving away from the axis, it's speeding up. So it's speeding up when it goes from here to here. Here it's going back towards the x-axis, so it's slowing down. Here it's going away from the x-axis, it's speeding up. And then from here to here, it's going away from the x-axis, it's speeding up. Okay, so anytime a graph of velocity versus time goes away from the x-axis, it's speeding up. All right, so one really fun thing to do is to practice using graphs and tracks. And this is a website, it's called graphtsandtracks.com. It's free. It's an HTML5 implementation of an old Institute of Physics app that used to be distributed in DOS, and it's totally cool. So I just want to kind of show you a little bit of it, and then I'm going to leave it up to you to go practice. This will really help build your intuition for understanding graphs of motion. So here's what it looks like. When you go to Graphs and Tracks, I'm just going to click on Practice, and you get a ball, and you can change the initial position of the ball. So you can put the ball anywhere you want, and you can change the initial velocity of the ball with a slider down here at the bottom. So you can make the initial velocity anything you want. And then you can roll the ball, and as the ball rolls, you will see a graph up here. This graph is showing the position versus time for the ball till it falls off the track. You can also look at the velocity versus time graph. So if you click that and hit roll ball, you'll see the velocity is positive and constant. Remember, the slope of the velocity graph tells you the acceleration. So this tells you that the acceleration was 0. It was not accelerating. It was rolling at a constant speed. And then you can look at the acceleration graph, and this one's kind of boring. There is no acceleration. It just rolls along at a constant speed the whole way. So what you can do, though, is you can have fun with this. You can put the ball over here on the edge of the track, and you can lift the track up so that when you hit roll ball, it speeds up. So then you can look and see what happens to the different graphs. So if you look, for example, at the velocity graph, I'm going to start the velocity at 0. So the initial velocity is 0. I'm going to roll the ball, and so the velocity increased, and then it stayed constant. Okay, so as it went down the hill, the velocity increased, and then it stayed constant. If we wanted to look at the acceleration graph, here the acceleration is a slope. So here we have a positive slope, so we should have a positive acceleration, and then we have no slope, no acceleration. The acceleration graph should be positive for a while, and then 0 for the rest of the time. And if you look at the position versus time graph, you can roll the ball, and you can see that as it speeds up, it curves. And then when it reaches the flat section, the velocity does not change, and so the slope does not change anymore. So that graph shows what's going on. So once you play with this a little bit, it's really fun to go to Challenges and start with the easy ones. And what they do is they give you a graph, and you can look at the position graph, you can look at the velocity graph, and you can look at the acceleration graph, and you can try to set up the track so that your ball, the motion of your ball, follows the path that's given. And it'll help to use all three graphs. So when you kind of think about it here, we have an object. It's starting at 50 meters. So I can tell that at the beginning here, the position is 50 meters. So I'm going to start it right here at 50. This is a straight line, which means it does not accelerate. So the track is not going to have any inclination to it. It's going to be a flat track. And if I look at the velocity graph, the velocity starts off, it looks like about positive 30. So I'm going to start the velocity about positive 30. And then I'm going to hit roll and see what happens. There we go. I set up the track so that the graphs matched. And once you get it, it says good job. And you can go to the next challenge, which gets tougher. Okay? So you can use that to practice and help connect motion with graphs of motion. It's a great tool. All right. Thanks for listening. I hope this was helpful.